FastMCP2's asynchronous task execution model enables concurrent operation handling through a lightweight task abstraction, allowing clients to initiate long-running computations while maintaining control over result retrieval and status monitoring. The client class serves as the primary interface, exposing methods like callTool with a task parameter that, when set to true, returns a task object immediately rather than blocking on completion. We're about to examine how this non-blocking pattern is implemented, starting with the client initialization and task creation, followed by the mechanisms for tracking progress and retrieving results. The code will demonstrate the core workflow, launching a background computation, performing other operations during execution, and finally awaiting the result when needed. From FastMCP import client. Async with client server as client. Hash start a background task. Task equals await client. Call tool slow computation. Duration 10. Task equals true. Print for task started. Tasked. Hash do other work while it runs. Hash get the result when ready. Result equals await task result. This code demonstrates FastMCP2's asynchronous task execution pattern using the client class. The pattern allows long-running operations to execute in the background while the main program continues processing. By passing task equals true to callTool, the client immediately receives a task object with a unique taskid, enabling non-blocking operation. The await task result call later retrieves the computation result when ready, implementing a producer-consumer pattern where the background task produces results while the main thread consumes them. The design enables efficient resource utilization by overlapping computation with other work, crucial for I/O-bound or CPU-intensive operations. The trade-off is increased complexity in error handling and state management, as the task lifecycle must be explicitly tracked. The pattern gracefully degrades when servers don't support background tasks, executing immediately while maintaining the same API, which provides consistent behavior across different server capabilities. This approach is particularly valuable in distributed systems where network latency or computation time might otherwise block the main execution flow. The task abstraction provides a clean interface for monitoring progress, handling cancellations, and retrieving results, while maintaining compatibility with both task-capable and non-task-capable servers through the returned immediately flag. Let's break it down. From FastMCP import client. Imports the FastMCP client class for interacting with the FastMCP server, enabling method calls like callTool and getPrompt with optional version specification. Async with client server as client. Establishes an asynchronous context manager for a FastMCP client connection to the specified server. The async with statement ensures proper resource management, automatically handling connection, setup, and teardown. The client instance becomes available within the indented block that follows, ready for making calls like callTool or getPrompt with optional version parameters. Hash start a background task. Task equals await client. callTool slow computation. Duration 10. Task equals true. Initiates an asynchronous background task by calling the slow computation tool with a duration parameter of 10, using the FastMCP client's callTool method. The task equals true parameter explicitly designates this as a background operation, allowing execution to continue without waiting for completion. The return task object can be used to track or manage the background process. Print for task started. Tasked. Prints a formatted string to the console indicating that a task has started, including the task's ID from the task object's tasked attribute. The output follows the pattern task started, task ID, where task ID is replaced with the actual ID value. Result equals await task result. awaits the completion of an asynchronous task, and retrieves its result. The task.result method call accesses the result property of the task object, and the await keyword suspends execution until the task finishes, then assigns the returned value to the variable result. This is a standard pattern for obtaining the output of an async operation in Python. FastMCP2's asynchronous task execution model hinges on the lightweight task abstraction, enabling non-blocking operations through the client interface. The workflow begins with client initialization via a sync with, establishing a managed connection. By invoking call tool with task equals true, you launch a background computation, immediately receiving a task object with a unique taskid for tracking. This producer-consumer pattern lets the main thread continue processing while the task runs asynchronously. The await task result call later retrieves the result, suspending execution only when the value is needed. The design gracefully handles both task-capable and non-task-capable servers, maintaining API consistency while optimizing resource utilization. The trade-off is explicit lifecycle management, but the abstraction cleanly encapsulates progress monitoring, cancellation, and result retrieval. This approach is particularly effective in distributed systems where overlapping computation with other work mitigates latency bottlenecks.
The client summons a task, yet the result arrives before the server finishes its first breath.